Okay, let's start with example 1, and we have dy dx equals x plus y plus 3, all of that squared. Now this is the example 1 in your book, but I do wanted to make some comments about this particular problem. So if you tried solving this differential equation without using 1.6, and again I want to emphasize this because I want you to see the power of the techniques in section 1.6. Now we know that if we wanted to, right, we could just write this twice, right, and then you can just triple distribute, right, and after distributing and combining all of your like terms using algebra, we're going to get x squared plus y squared plus 2xy plus 6x plus 6y plus 9. And of course, dy dx or y prime. And if you tried to separate your variables, right, using, well, in section 1.4 you learned how to separate variables, this would get very, very crazy. I mean, it just, you could multiply both sides by dx, you could try to factor and, put all your x's and x's and y's, but I mean, in the end, you're not going to be able to separate your variables. So again, that's why we have section 1.6, and let's use substitution. And again, on your exam, I will say solve the differential equation using, separating variables, blah, 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 or by substitution. So we don't want to do this, okay? Not for this specific problem because it's not going to work out. We want to use section 1.6. So I'm going to let my v be this expression. So let v be x plus y plus 3. Okay, so remember from the previous video, right, we let v be an expression, and then we solve for y, right? So if v is that, then, because we're going to use this equation, then y is equal to, well, let's see, y is equal to v minus x minus 3. Okay, so I have this equation. And now I can take the derivative with respect to x, on the left and on the right. So again, I'm really doing, okay, dy dx, right, or ddx of y, and I'm finding the derivative ddx, right, of v minus ddx of x minus ddx of 3. And so when I find this derivative, I get, okay, this is just dv dx, right, or v prime, minus, let's see, 1, and then the derivative of a constant is 0. So I'm left with, again, if you wanted to write v prime, that's fine, or y prime. It's up to you if you want to use Leibniz notation or not. Okay, so this is what we have. Let me box that one, right, or this one. Okay, so now that we have this information, now we want to transform our equation. Let me just refer to it, right? This guy, I want to transform this into a function of v and x, right? Using the 3 equations that I just, that we just solved for. Okay, so let me maybe make this a little bit smaller. So, okay, so I'm going to, I'm going to use that equation. And so I have dy dx. Okay, well, what is dy dx equal to? Well, dy dx is dv dx, right, minus 1. So I can say, dv, well, this is fine. Okay, just to, let me just rewrite this again. I think it'll be easier to translate. Okay, so I move this up. Okay, so now dy dx is dv dx minus 1. Okay, so that's done. And now we can substitute, right? We called this guy v, so that's just v squared. And we have we just right, this is the transformed differential equation, right? This is our function of x and a v, or v and x. So here, now if we look at this differential equation, we can add a 1 to both sides. So we have dv dx equals 1 or plus v squared, or v squared plus 1. And so now we can separate our variables if we want, since this is a separable equation. And so I'm going to, let's see, we can multiply both sides by, well, actually I can, well, let's just do dx. So if I multiply by dx, I get dv equals v squared plus 1 dx. And I'm going to divide both sides by v squared plus 1, right, because I want it with my dv, and then my dx is just hanging out. So I was able to separate variables, right, after the transformation. Okay, so let's abbreviate, after the transformation. Because now we just use section 1.4, right? We use what we know. Well, we can definitely integrate both sides. So if we integrate both sides, this guy looks like, let's see, 1 over 1 plus v squared. Well, I'm thinking of the natural log, but it's actually not the natural log. If we look at the inside cover of your book, or, I mean, you can just look at the example 1, since it's written there. This is number 17, the inside cover of your book on elementary forms, right, your table of integrals, and it's just in terms of du, which is fine. But this is, whoops, it's not what I wanted. This guy, right, this is your a squared plus u squared, and we can just write that out. That's going to be, right, 1 over a tangent inverse of u over a. And if we write that out, that's just tangent inverse, right, of v over 1, which is just v. And then, of course, we add our constant of integration, and then this guy. And the integral of dx is just x. So we just have x. Okay, so our goal, right, is to find the solution to this differential equation. And again, we just transformed this equation with v and x to help us obtain a separable equation for this specific problem. But we have to go back to our original problem. So recall, we substituted an expression, right? We let v be x plus y plus 3. So let's solve for v. And we can, actually, before we do that, we can just quickly move this c over, right? It's just some constant. Now, if I take the tangent inverse, or the tangent of both sides, right, because I want to solve for v, I'm going to get v equals the tangent, right, of that, whatever that angle is. So I have v, but what was our v? I let v be x plus y plus 3, and so tangent of x minus y, right? Just like when you first learned how to integrate an integral in your integral calculus class, you use u substitution, but you have to go back to your original function in terms of either x or y or z or p. So finally, we can see our solution to our differential equation, right? It's right here. So if we can just say y of x, it's a function of x. And let's see, tangent of x minus c, and I can just subtract that x and subtract that 3. So that is my general solution to this differential equation, because I wasn't given an initial condition. So that's the idea. Again, it's a little bit, well, I don't think it was too long, but again, that's the idea.